So welcome. This is the last time we'll, I guess, formally meet on this module. I have graded the exercise 2 that was due a week ago, and you should have it. You should all have it back. The exercise 3 is due today, so I'll start grading it sometime soon. And then the work that we're doing on now is due in a week's time, and I'll sort of grade that and follow up on getting grades assigned as we move through. As you work on these homeworks, please don't hesitate to reach out to me in Canvas or by email. We can also get on GoToMeeting for any impromptu discussion if any of that's needed. So yeah, it's not completely over, but this is, I guess, the last time we formally meet, and it's been a really rushed and I hope beneficial for you 4 weeks, because yeah, there's a lot of material here, and I hope by the time you've worked through these exercises, you've learned a lot. So there's a question here that says, would you mind going over question 9 and exercise 3? Was your question a little bit more specific than that, or I think it was?
It was.
Go for it.
My question was, how are we defining the main stem for question 5?
Okay, so here I've got here I've got the exercise, watershed delineation exercise 3 loaded up, and I said to determine the length of the main stream and Logan River drainage area based on the delineated stream network. So there we've got the delineated stream network, and I didn't really define the concept of mainstream. What I probably should have said the longest stream or something like that, because that's a common definition of mainstream. So what I was anticipating for you to do was to identify the properties of the uppermost reach, which is that one, and that was the one that I put a little red box around in the exercise. And you can look at these attributes, and I think in the exercise I drew attention to this one, which is D out start. That means that's the distance to the outlet from the start of that reach. So from that point there, it's the distance all the way to the outlet. So that's actually the mainstream length. Look at some of the other ones. You can see the distance to the outlet from the midpoint, that's sort of halfway down. The distance to the outlet from the end is 58150. If we then click on the next link down, you'll see that 58150 is the distance to the outlet from the start. So those sort of things should work out, and there should also have somewhere been a length of the reach involved, and the difference between the start and the end should correspond to the length of the reach. So that's what I had in mind with the sort of length of the main stream. I guess you can also look at the most downstream reach, and if I can get it to click on the reach rather than the catchment, here the distance to the outlet from the end is 0, because the outlet is right there. So then there was the question in chat said, would I mind going a bit over question 9 and exercise 3? So by question 9, do we actually mean what I had as section 9 there? I don't think they were quite. The question 9 says prepare a diagram that shows. So did you want me to answer the question that about preparing a diagram, Ben Huis? If you could type your answer in chat or speak up if you've got audio. So was it the question about the diagram? Was that the one that you wanted? Okay, so a diagram that, so a table that reports for the 5 stream lengths, the link number, downstream link number, upstream link number, and so on. So, and then a diagram that talks about the connectivity. So what I think I had in mind is, I'm trying to think if I've got a slide anywhere that addresses that I've used in the past. But the table might have the column link number, downstream link number, upstream link number, and then you'll have a row for the one link, another row for the next link, another row for the third link. And you should be able to show that the downstream link number in the downstream link column is the same as a link number in a different row. And you might just draw circles around, say this to that, and say that this relationship indicates that that link is downstream of that link. So I was thinking of a table with sort of circles around some of the numbers and arrows between them and explanations to show how the connectivity is encoded. There's also a table of the sub-watersheds, or the sub-watersheds are effectively a separate data structure because they're represented as vector polygons, these sort of things. And if you look at, maybe we should be looking at their attribute tables. So you've got an attribute table of the sub-watersheds, and you've probably got an attribute table of the stream reaches. So we can open that attribute table and remove some of the columns that we're not interested in from this, just to be reporting the columns that we've got identified there, and try and show the sort of two tables side by side. And let's actually do some of that. So let me zoom in and try and identify the watershed that I think we were working on was Spawn Creek, which was kind of around there. I've selected too many streams. Let me just take another shot at selecting fewer of them. Possibly I've selected the right ones. So if I show only the selected ones there, and I show only selected ones here, I've got some of the ones on the left-hand side shouldn't be selected because I was a little bit careless in my selections. But if you show just the things like the link number, the downstream link number, and the upstream link number, you can see that link number 181 has downstream 229, which is not in the set. So link number 181 must be the most downstream. Link number 173 has link number 181. So circle that and show that this record says that this link is downstream, and you should be able to see that with the labels on the map. It says the upstream 2 from number 173 are 5 and 29. There is 5, 29 is hidden in here somewhere. So sort of circles and arrows on this this table to show those relationships. And then also in this column is watershed number. So there's a watershed number 181, and that should correspond to the grid code here, 181. There's a watershed number 173 that should correspond to this grid code 173. So with those two tables side by side, you could show that, you could say that this column there maps onto the corresponding values in this column in the watershed table. That's more or less clear, I hope. Okay, any other questions on any of our current homework? There have been a few folks who were having trouble with the Towdem installation. Everybody who was having trouble has at least reported back to me that they had it sorted out. Sarah, you were having trouble that's related to showing things with a classified scale. It's I don't know how to solve that one, but it works for me, which is not a very good excuse. So I think I responded in an email that you can maybe just use the continuous scale rather than the classified one to show that. I did put in Canvas here under the, I guess I should log in. Under discussion, some of the, I opened a discussion on Towdem problems, and I was hoping that, well, I explained what some of the things to try and do, and then this is the answer that Josh figured out and sent me an email, so I put it there. And if any of you are still having Towdem problems, look at that. And there's a new discussion here that I had not seen before. Okay, so this is somebody encountered the following when running the Python script from idle, and an apparent licensing issue. So yes, so I know the answer to that because somebody emailed me about it, and the way I found out the answer was I went to Google and said ArcPy spatial analyst license, and came up with this web page. And so I'll copy that web page. But if you scroll down there, it's got a suggestion that says that you can put ArcPy checkout extension spatial. So let's just quickly note that. Look at that web page, and specifically this command. Now, I don't actually know whether that works because my computer doesn't seem to have that problem, but if one of you can sort of verify that it either does or doesn't, that would be helpful. So I'll put that as a reply for everybody. Anything else before I get on with the topic of the day? Okay, so I wanted to talk about height above nearest drainage, a bit of the theory that's behind what we're actually doing. So let's get this presentation going. So this is work that I've done with a group at Texas and a group at University of Illinois. It was done a couple of years ago. Now we've just got some papers out on this, and I'll give you the sort of gist of the idea here. So we're going to talk about continental scale flood inundation mapping from the National Water Model, then calculating the height above the nearest drainage. You've already sort of seen the tool for doing that, but I'll talk a little bit about more of the theory about how that tool works. Then using hand to determine reach average hydraulic properties, which is a really useful part of it because that will then help us with the rating curves that can be used in flooding. And then some of the further considerations that you have to worry about in applying this. So the general idea behind height above nearest drainage is that flooding occurs when the water is greater than the height above the bottom of the stream. So if the height above the nearest drainage from this address point where there's a house is less than the flood depth, then you're going to have flooding at that house. If that height is greater than a shallower flow depth, perhaps normal flow depth, then you don't get flooding. It's a really simple idea, and it may be used to determine effectively the extent of flooding. So that's used with the National Water Model. So this is a slide that comes from David Tarboton, and it shows the sort of animations that the National Water Model is producing. And it is showing the stream flow in the different reaches of the 2.7 million reaches in the National Hydrography data sets. And those are being simulated and forecast every 3 hours. And but that's just the discharge that's coming out of this model. And there's a question, okay, so can we map that onto the area that's actually potentially flooded? So the general idea is that you take a discharge forecast from the National Water Model. You need to transform that into depth with a rating curve. So a rating curve is a function that says if you've got this discharge on the x-axis, that's the depth will be on the y-axis. Then once you've got that depth, you can go back to the height above nearest drainage idea and create a flood inundation map from that water depth. And then you can assess the impact on people and property. And in the last part of this exercise, which I'm hoping to get to by the end of today, I'll show you where we can take the Onion Creek address points and look at height above nearest drainage and identify which ones are less than or greater than a threshold. So the National Water Model uses the NHD plus medium resolution reaches and catchments. So there's 2.7 million of them. They're about 3 square kilometers on average. They produce flows that you could visualize like that shown on the right. It's based on running actually a gridded model across the country. It's and then you go from these grid cells onto the catchments, which are irregular catchment shaped polygons using area weighting, much as the same we did with Thiessen polygons. You can think of each of these is effectively treated as a polygon, and the intersection with the catchments is used to determine the area weighting for those grid cells. So the way that's implemented in GIS is each stream reach has a discharge. That's what you get out of the National Water Model. Each stream reach has a water depth calculated from the discharge, and that comes from the rating curve. Each stream reach is going to need a rating curve, and we'll talk about how to get that. Then each stream reach has a unique identifier. That's a sort of GIS information model part of it. Each catchment has a unique identifier for the reach to which it drains. So we've been seeing, as we were looking at the results we got out of exercise 3, there were the catchments with an identifier, the reaches with an identifier, and you can identify the catchments associated with the reach. Each grid cell belongs to a specific catchment. So it has the identifier of the catchment it is in, which effectively is also the identifier of the reach it drains to. And because the height above nearest drainage is a gridded result, each grid cell also has the height above the nearest drainage. So if you think of all of those 5 things, this is really just sort of stating what we've got once we've done all the processing to assemble this information. Then evaluating inundation becomes fairly straightforward. You just have to ask the question, if the depth of water associated with that reach ID is greater than the height above the drainage associated with that ID, then the inundation depth is the depth of water minus the height you are above the drainage. Otherwise, the depth of water is 0. So you can take the streams, the catchments, so the streams, the blue lines here, the catchments, the sort of shaded colors, the height above nearest drainage, you put them all together. For each unique identifier for each reach, you've got a depth, and you can identify the grid cells that are shown here in blue that would be inundated, and you can work out what that inundation depth is. So we'll actually do that for one of the catchments in the exercise. So here, if you zoom in on the results with some hypothetical depths associated with each of these reaches, you can see what the inundation depth raster might look like. A lot of the area is 0, but the area around the streams can be flooded. It's important to point out that this is an approximate approach because it neglects many of the details. I mean, there's probably a few people out there who have worked on river hydraulics and overland flow and say, hey, but you're not taking account of all of these assumptions. But for the models that require a lot of detail, they often have inputs that are required that are hard to obtain. And this sort of fairly simple approach, we're, at least when we're promoting this method, are saying is a good way to get sort of screening level real-time flood maps, and it's worthy of evaluation and use for that purpose. Is recognizing that it's approximate, but then all models are approximate, and getting something out quickly is often good. And it's premised on a good elevation model and consistent stream raster. If your elevation model is not very high resolution and your stream raster is not very good, well, then it's going to be garbage in, garbage out. So that's actually motivating the whole nation to try and gather much more higher resolution data along our streams to help with this. And the workshop that I was at in Texas last week was actually discussing how to get high resolution, they called it topography bathymetry, topobathy, to improve this sort of work. So here's an animation that Jing Zheng, who was the PhD student who worked on this at Texas, put together. So I'm going to do that, and let's just stop it briefly and explain what's going on here. So this is Onion Creek, and we'll be doing the example for Onion Creek, and this was a flood that occurred in May 2015, and these are the discharges that occurred in Onion Creek, probably at the outlet, and then here is the number of addresses flooded. Height above nearest drainage approach has been applied over the whole watershed, and there are houses each with an address point, and as you go along and the discharge goes up, you'll see the number of houses that are modeled to be flooded goes up too. So let's let this thing go again. So you see in the sort of zoomed in area where the peak goes up, the blue area expands. And the red dots actually show the houses that would be flooded at that discharge. So let me see if I can get it to stop just in the right critical place. Click the wrong thing. Okay. There. Okay, so there we go. I've got the animation round about near this peak, and it's showing all of these red dots or houses that might have been flooded. And here in this little box that's been zoomed in here, you can see the river has expanded, and these poor houses here are underwater. And I mean, a lot of this work was motivated by these houses really getting flooded in the middle of the night, and people's property and some lives being lost, and it was a pretty tragic situation. So calculating height above nearest drainage from a digital elevation model. So we've learned about the D-infinity approach, where you have the routing of flow down sort of perpendicular to the contours, with the sort of spreading out and proportioning of flow between downslope neighbors, to effectively make our flow go perpendicular to the contours rather than biased off to the side that might be if you use the sort of D8 approach. So when you turn that around and are thinking about height above nearest drainage, you're at a point on the hillside here, this blue dot, which would correspond to this red square here. And there's a number of quantities you might be interested in. You might be interested in the horizontal distance to the stream, or the vertical distance to the stream, or even the distances up to the ridge if you're interested in some sort of ridge processes or hill slope processes. But the height above this drainage is the vertical distance to the stream option. And that's evaluated by effectively looking at all of these flow paths, where they actually hit the stream as it's been mapped from the DEM, and tracing back up to this point, and effectively doing some sort of a weighted average over where all of these hit the stream. So it's a weighted average over multiple flow paths, and that results in a sort of a smooth surface for height above nearest drainage, which I think actually is good, because if you think of this water that originates here, this point on the stream is going to be lower than that point on the stream, and the height you are above the stream should probably be some sort of average of the stream nearby that it flows to, not just one specific point. So the way it works is you start with setting the height equal to 0 along the streams. That's the streams of the target input set. So we mark all the streams as 0. You mark the remaining grid cell as ready if all of the down results are available, and not ready if the down results are not yet available. So for example, this cell next to the stream here would be marked as ready because both of its downstream results are available, but this cell way up on the hillside here would be marked as not ready because you can't calculate that. So there's an initial pass across the grid that identifies all of the ready grid cells, and it puts those in a queue. By putting them in a queue, it then starts to allow parallel processing, because different processes can work on, can just pick things off the queue and work on them and not worry about, and another process can work on another point on the queue without, so they can be doing things at the same time. So it's kind of like you've got a number of homework assignments and you can just pick any one to do. And if you were working as a team, you might spread it out. That wouldn't be a good educational model to encourage, but if you want to be efficient about solving the problems, that's how the computer, I mean, you don't have to have, each processor on the computer doesn't have to do all of the work, but students have to do all of the work. So, looking at this, this grid cell, it perhaps has a flow direction like that. There's two elevations, the elevation of 435 at this one, a little bit lower, 435.35 at that one. The two proportions, there's a proportion of 2/3 going up, portion of 1/3 going up diagonally. So the elevation difference is evaluated in each direction. So the elevation difference from there to the north is 0.92. The elevation difference to the diagonal is 1.13. So the height of this above the drainage is calculated as 2/3 times 0.92 plus 1/3 times 1.13 is 0.99. So fill that number in. Then immediately this is filled in, it says, okay, some of these neighbors now may be available to be calculated because they have all of their downstream results available. So they would get put on the queue and eventually they would get computed. So the computer proceeds like that. So maybe you're at a point down here. So we evaluated this 0.99, that 0.95. You've got a 2.64 and a 1.88. And those are the only two that this one depends on, because this one flows from there to there. And the proportions are 0.6 and 0.4. So, and this height here is 1.88 and 2.64. So then you do again, you calculate the deltas involved. So the delta for going from there to there is 2.1. The delta from going from, I know the 3 is immediately to the north. The delta in the direction 4 to the northwest is 2.74. and you evaluate this height by the 0.4 times that 2.74 plus the 1.88, that's the height above there, and then this 0.6 and the 2.1 plus this 2.64. So that's how the sort of weighted averaging is working based on the proportions. And that'll get evaluated, and eventually you'll have evaluated all of these heights above the drainage, and this shows the actual elevations for this little grid and the height that you are above the streams for that little grid. So it actually becomes now a relative digital elevation model. It's relative to the location on the stream. So this is what it looks like for Onion Creek if you use this nice sort of gray, brown to blue color scheme. Yes, go ahead.
Is the height of the stream from the top of the water a base flow or like a 2-year recurrence interval, or what do they use?
Well, ideally you should have the height above the bottom of the stream bed. So it should be at zero flow if you could ever get zero flow. Now, so the height of the thalweg. Now, oftentimes that's not available, and our digital elevation models actually are recording the water surface. But the work with bathymetry is actually to develop LiDAR that will penetrate the water. So there's the green beam LiDAR will penetrate water. The red beam LiDAR, that's the less expensive one, that's therefore used more, does not penetrate water. But if you're trying to get the beneath water depths, you have to go for the green beam LiDAR, and you also have to have clear water. If it's very turbid, then the LiDAR is not going to penetrate it regardless. So or they'll actually, if it's turbid, they'll put an acoustic Doppler current profiler, which will use sound waves to effectively measure the depth. But that requires effectively some sort of a boat to go on the water to do that. And it can be a little boat. It doesn't have to be on a large water body. They'll go in a real boat, but they have these little sort of almost meter-sized boats that are radio controlled or controlled by some ropes that just have that instrument on it. Yeah, but it should be the underneath the water topography. So that's how you calculate height above nearest drainage. Then this is the cool part, thinking about reach average hydraulic properties. So some of you've probably seen the sort of work that people have done with trying to route flow down rivers, the HEC RAS or HEC RAS program that has a whole bunch of cross sections. What this approach does is, instead of taking cross sections, tries to take the digital elevation model and the height above nearest drainage and use that entirety along a reach. So we're looking to have a table and build up the reach hydraulic properties. So here's a stream reach, and we're saying that you might think of the water within it at a certain depth as being represented by this prism. There's a depth H, there's a surface area of that prism, there's a volume of water that's in that prism, and there's a length. And the cross-sectional area average over that reach would be the volume divided by the length. And no matter how irregular the reach is, that becomes a sort of a reach average cross-sectional area. And we think that that's better than a cross-section, because a cross-section is just a specific point in space and it's neglecting what's going on in between. You can take the bed area divided by the length and you get a reach average wetted perimeter. You can take the surface area divided by the length, you get a top width, and then the cross-section divided by the wetted perimeter is the hydraulic radius. So those are some of the things that you need to effectively use in hydraulic routing. So if again we go to now for each catchment, so you've got a stream reach and we identified the catchment that drains to it. Now we're going to the catchment because that's all of the area that drains to that reach, and the water may flood out over that area. We don't know the extent to which it's going to flood out over that area, but we need to look at all of the grid cells in there. And for each height, we first identify the cells where the height above the drainage is less than our height. And those are going to be the cells that are inundated. Then each single cell has a plan area, the cell size dx by dy. And so the surface area, this AS, is the sum over the cells where the HD is less than H of that single cell area. So it's just summing up the cell areas. And mostly the cell areas will be the same. In this calculation, they are subtly different because we did allow the opportunity to work in a geographic coordinate system where the cells get narrower as you get towards the North Pole. The bed area is the surface area times the square root of 1 plus the slope squared. Now this comes from the idea that if you've got a sloping surface, you can think of the length of the hypotenuse of the triangle you might have if you've got a horizontal surface and a vertical surface is 1 in the horizontal direction, slope down in the vertical direction, 1 squared plus slope squared, square root gives you the length along the slope. So that gives you the bed area of a sloping cell based on its slope. So it approximates each cell as a sloping plane. Then you can get the volume of water is, again, summing over all of the cells of the area of the cell times the height minus the height above the drainage. So you can evaluate those things from the GIS. Then you just evaluate these things, the cross-sectional area, the wetted perimeter, the top width, and the hydraulic radius. That's information that can be pulled directly from the GIS. So here's an example of how that actually works. So I took a particular catchment, and we had flow lines here. And there's a little bit of complexity in here because we're looking at the difference between the terrain flow lines and NHD plus flow lines. But just think of the terrain flow line there for a minute. We've got you can map the height above the nearest drainage, and if the height is 1, you can evaluate the surface area, the volume, the bed area, the length. The length actually comes from the length of the reach. So those you can get from sort of spatial analyst calculations. Remember, we've done threshold calculations where you say this elevation greater than a threshold. We use that to identify the top of the mountain. We also use the differencing to identify the internally draining areas. Exactly the same concept. You can evaluate these things for different heights and put them in those formulas to get all of those quantities. So if I'd wanted to make this exercise even longer, but I didn't, I could have actually had you go through and do that. So you end up getting results like that. Then so here's an example where you've got a catchment, it has a certain reach, it has a drainage area. Now you need to know something about the hydraulics. So the assumption that's made here is that it's going to be uniform flow and Manning's equation. So that's the probably fairly gross approximation that's involved here. You have to get a Manning's roughness. So there's that doesn't come right out of the GIS. You need to use other information to do that. You can get the slope out of the GIS. So then you've got the slope, hydraulic radius, cross-sectional area, and you can, for each height, you can work out the discharge and have a discharge stage relationship, and that's effectively the rating curve for that creek. So you have the forecast discharge, it gives you the flood depth stage. Once you've got the flood depth, you can then map the inundation for that particular catchment. So let's pause and see if there's any questions there, because that's an important set of concepts. And those are the sort of key assumptions that are underpinning this approach for flood inundation mapping. So anybody with any questions, let's pull the chat up so that I see it if there is any. Okay, not hearing any questions. I will charge on. So there's a few other things you do need to be concerned with. Deriving the terrain aligned flow network. So on these slides earlier, I said there was a bit too much complexity going on. The black line is what the National Hydrography dataset maps for the flow lines. They aren't exactly in the bottom of the valleys, and that causes trouble. So we actually need to map the terrain flow lines for this approach to work. So the way that we did that is we took our D8 flow directions, we went to each channel head, and instead of using the NHD plus flow line, we basically created a flow line by following the D8 flow directions. And we're following D8 because we don't want it to spread out. And we're using the D8 flow directions that have been calculated with TAUDEM that takes advantage of some of the more advanced things like routing across flats. But the basic idea is you've got a channel head, and while the National Hydrography stream may say it goes like this, if you take this approach, it follows down the valleys. So the black line here is the NHD stream. The blue line is what we've done with the flow line. You can see over here, there's actually a difference. And to try and evaluate the height above nearest drainage to this stream here that's sort of cut the corner a bit and going across the contours would be problematic, because this water is actually flowing south away from the stream down to that point. So and that all comes about because this is calculated with the highest resolution digital elevation model available, which is a 10-meter cell size. The NHD plus was evaluated from a 30-meter cell size. So just think of multiplying each of those cells by 3, and then that's not actually that bad an approximation. But you do have to pay attention to that. So this is the sort of result that you get. You've got the flow lines delineated from the digital elevation model going right down the valleys, and you can sort of color and height above nearest drainage for different thresholds. Sometimes you get problems with the digital elevation model due to road or railway crossings. There happens to be a railway crossing along here, and you can see in this hillshade that it blocks the river. So if you actually try and map the streams from the DEM, it doesn't flow through there, but it gets deviated all the way up to the north until there's a low point over here, and then it sort of finds its way back. Well, that's obviously not the way the water goes, because really there is a railway bridge and the water does go underneath it. The NHD plus flow lines sort of follow that direction, but they miss the detail. So what we have actually done here is devised a procedure to use the high resolution NHD flow line. So those are the blue lines on this map, not the red one, that actually follows that path a little bit better, and find the direction of flow depicted by these arrows here, and then developing a process that I'm calling etching or soft burning that traces down these flow lines and lets the elevation never go up. So if it goes along, and if it's in this valley here and then it suddenly encounters that barrier, it just lowers the elevation, sort of pushes the dominoes over. And then when it starts going downhill again, it'll flow on the top of the surface. If there's another bump up, it'll push the domino over. And so there's enforcing the digital elevation model not to increase along the flow path. So this is what it might happen if you're looking at the data. You've got, this is the DEM, this is the flow line. The flow line comes along there, and there's these two cells, or this one that's high, there's an elevation of 40, then 51, 43, 39. Well, these two get lowered down to be 40 and 40. So it sort of punches through that hole there. So that's what's actually done here. And this is the reason why for this exercise, I gave you the digital elevation model for Onion Creek rather than have you get it from the national elevation data set, because we did this process on that first. So Onion 3, it was the sort of third step in the process. That's why it ended up with that name. It would have been would have made the exercise a whole lot longer if I'd sort of made you go through the process of doing that. But the effect of that is that the height above nearest drainage sort of stays much closer to the streams in this area, rather than without it. It sort of says that there's a whole bunch of flooding out here, which is way away from the stream, that doesn't look realistic at all. So that's an important thing to do to improve the data. So these are the grid cells that actually got changed. So grid cells only get changed along the streams. All on the hillsides here, they are left unchanged. Many times the changes are small, but where there's a barrier like this, the change can be quite big. In this case, getting up to 14 meters, because the railway crossing was relatively high above the river, and the DEM was the top of the railway crossing. So this slide just sort of summarizes all of these things. Hand is a special case of Towdem distance down. It's been suggested as a way to rapidly approximate real-time flood inundation. It serves to support flood inundation mapping where the data to do hydraulic calculations is limited. There's details of the hydraulics that are neglected and flow over floodplains, but a more detailed approach demands hard to obtain and uncertain input, so it may be helpful for sort of screening level mapping. There's an approach to approximate reach scale hydraulic properties, which is really handy because it avoids all of the business of trying to get cross sections. It's premised on a good digital elevation model that should represent bed elevations to the maximum extent possible. And we need to research ways to align and reconcile the elevation and the hydrography. The obstacle removal approach is really just a bit of a sort of a quick band-aid fix. It'd be good to have the data sets we get from the national data sets to be consistent without those sort of problems. It was calculated across the whole continental US using 10-meter resolution digital elevation model and NHD+. And it could actually exploit high resolution LiDAR data in areas where accuracy is critical. So you could go and if you've got better than 10-meter data for a particular catchment, you could just calculate that catchment at the 3-meter or the 1-meter resolution and then leave the rest the same, and just sort of insert that result in. So that's one of the approaches that you could use to sort of have this get incrementally better as more and more data becomes available. So that was, go ahead.
This is Christina from USU. How does this perform in groundwater fed systems?
Well, it'll perform as well or as poorly as the model for flow is represented. So this assumes that what the hydraulic model is giving you is a surface discharge. If you've got a stream that's sort of disappears into the ground and then it appears back out again, it's not going to, and you've just got a single value along there, it's not going to represent that. It's really targeted at flooding, and for flooding, the amount of hyporheic flow is probably pretty small as a fraction. But yeah, good question. And if you're really sort of dealing with low flows, well, low flows have other considerations. The inundation area is not necessarily, well, I'm going to say it's not that critical for low flows, but it is, because the amount of surface area you've got is an environmental consideration. It's the surface, the water surface that's available for evaporation, for heating to go into the water, and all sorts of things, aeration. Yeah. Oh, there's a question in the chat. All right. How can we consider the effects of dams along with streams? So the National Water Model has a large number of dams in it. Let me get out of here. well, I guess I don't really need to show the picture again. Where there's a dam, there's some sort of a routing model for it. Maybe it's a level pool routing that says as the dam gets higher, there's a storage discharge relationship for that dam. That would be separate from the channel routing that might use the Manning's equation and the rating curve approach that we've got. I mean, there is also a question of, well, where did those discharges come from? Those discharges had to use some routing down the streams, which had to use some information or some assumed information about the channel geometry. The National Water Model actually has assumptions of trapezoidal channels, and then when it gets to a certain level, it goes out over a floodplain. Well, that's not exactly what's there, and height above nearest range is giving us refined hydraulic geometry. So there is an opportunity for maybe improving things by taking that geometry and feeding it back. Where there's a dam, using the real information about the dams, and for the operational purposes, using the real discharges. So the whole idea is that at the National Water Center, the sort of secure facility, you'd have the information from the dam operators fed in so that you know what the dams are actually releasing. Sometimes that information is not publicly available for researchers because there's concern over there's concern over security of dams. There's also concern with hydropower operators not wanting to have their competitive information about how they generate hydropower sort of discovered by other hydropower operators and perhaps a different electric utility. So that information isn't always public, but it is available in the sort of operational center where they are doing it for real. Any other questions? Okay, so I'm going to use the remaining time to do some of this in ArcGIS. So I was going to bail from exercise 3. So let's not save whatever I did there. I'm going to close my slides. Open. So I have here in my ArcGIS work folder, I have the Onion Creek zip file that we had. I've also got the DEM to watershed program that we were working with last time. And I've got one here for Onion Creek where I've gone and changed the names. And I'm going to start from that one to sort of make things go along a little bit, because you don't want to see me doing a bunch of editing of a text file. But I'm basically going to start from the exercise that's on page 11 where it says applying to Onion Creek, because all of the stuff of applying to Little Bear was the sort of things that I demoed last time and got a bit snarled up because my computer was getting the wrong data some of the time. So hopefully I won't get plagued by those errors today. We will see. So open ArcMap. I'm going to go with a new map, blank project. I'm going to put it in the ArcGIS work folder where I've been doing all of this. I'm going to name it Onion. I'm going to let it create a new folder for that project. And I'm going to go to my folder. So there's the folder Onion. I'm going to put the DM to watershed Python program inside it. I'm going to take the zip data that I had that's got the onion3.tif and the hand geodatabase and copy that information into the Onion folder. So right now all it has is it's got this Python program I put there and the files you get when you start a project. So if I paste the the TIFF file there and the hand geodatabase there. Now I should be able to load some of this data. So let me go to my catalog here. I look at the folders. There's Onion. So I could load the DEM. I can open the height above nearest drainage geodatabase. So here's the question about pyramids. I'm going to just say yes. Okay, I should probably let it finish, or it's going to make sure I let it finish before I do the next thing. Maybe I should have said no to the pyramids. So this is actually a fairly large digital elevation model because it's 10-meter resolution. So there you can see we have the sort of grayscale that represents the digital elevation model for Onion Creek. If I wasn't being quick to try and do it in an exercise, I would go and make it a different color. But I'm going to go in. So there's the hand geodatabase. There's UTM-14. And this is information that's already, well, this is from the National Hydrography data set. We're not going to worry about the National Hydrography data set because we're going to actually calculate everything ourselves. I thought for this exercise that we're going to use the Python script we developed in the earlier part to calculate ourselves, to be doing some sort of Python programming usage. So I'm going to just put the outlet on the map. And I'm also going to put these address points on the map. So these are all the houses that we're going to worry about whether they get flooded or not. Let's make the outlet a different symbol so that we can see which of those dots is the outlet. So that particular, put it above there. So there is where the outlet is, and there is where all the houses are that we are going to be considering. So I have the script that we worked on last time with it ready set up for Onion Creek. So I'm going to just edit it with idle. And so the only difference between this one and what was actually given to you is changing some of these names. So these lines are all changed, but here where it says output directory, I've got C users DTARB documents ArcGIS work. And I didn't, when I was doing it earlier today to check that it all worked, I used Onion Creek. So I'm just going to put Onion there, so without the creek. Then I went through and put in the name of the digital elevation model that we're working with, the name of the location where our gauge is. Now, this is a name that's relative to this directory. So inside Onion, there's the geodatabase, the UTM-14 feature dataset, and outlet. So you can see that back in ArcGIS in the catalog here. You've got the Onion folder, the geodatabase, UTM feature dataset, and then the outlet feature. So make sure that the code is going to find that. I've changed the threshold to 50,000, and that's, I just determined that sort of experimentally. I didn't go through the process of doing the constant drop approach because I wasn't doing this with Taudim here. 50,000 gives you a drainage density that's coarse enough, that's got a few enough catchments that you can actually sort of see what's going on. The snap distance is, in case this outlet is not right on the stream, it's going to move it up to 100 grid cells to get it onto the stream. So then the code is all the same, but I've gone through here and used a different set of file names. So the filled digital elevation model, I've used onion3fel.tiff. For the flow directions, I've got fdr.tiff. For the flow accumulations, I've got fac.tiff. So it was fairly tedious to go and edit those. So this is where this is a sort of useful program, but it's not necessarily all that well structured. A more general approach would actually construct those file names itself, and you would just have to control it at the beginning. So maybe this, maybe we decide that we're going to have FEL, FDR, FAC as our standard names, and they get appended automatically. And that's what's happening in some of the TAUDEM work. But I didn't want to make this code any more complicated, because for many of you, this might actually be the first Python code you're looking at. I wanted to sort of keep it simple and focused on the part of the work that we're actually doing. So I can now run this Python script as we did last time. So let's hope that it all works. We have to save the little change that we made. So we had the question about the spatial analyst license. Somehow, yeah, the licensing part of this is a little bit of a mystery, because you can actually run it without ArcGIS being open, and at least it seems to work for me. I have never just come in and sort of had ArcGIS closed for a long time and run it, because I always open ArcGIS to kind of look at my data, and then I run it. So maybe it's got a certain timeout procedure for the licensing, but you can actually put instructions in this code to open and work with licenses. So here it's stepping through. It's done the pit fill, it's done the flow directions, it's now doing the flow accumulation. Then it'll take the outlet and snap it onto the flow accumulation map, and then it'll do the delineation of a watershed. So I named that Onion 3W, effectively just delineating one watershed for the whole area. Then it's going to, here's a little bit of interesting logic where it's taking the flow accumulation greater than the threshold being 50,000 grid cells, and the Onion Creek watershed greater than 0. So it's only mapping streams within our watershed. So that was the rationale for first delineating the watershed, and you'll see that the result is only upstream of the outlet because of what we did there. Then it converts the rasters to links. It creates the catchment grid and converts it to catchments, and it's done. So I can then go and do a refresh on the folder, and I should see there is all my results. So for example, I've got flow accumulation. I could add that to my map, and I would see what it looks like, and it's kind of black unless I adjust the symbology, and maybe I'm going to adjust the symbology to classify and pick a sort of a blue and switch it around and put in numbers that are maybe sort of 300, 1,000, 3,000. I should probably I think I mapped things at 50,000, so let me put 50,000 in there, and then turn those address. So there's the flow accumulation, and at this zoom level you don't see much, but if we sort of zoom in, you'll see how it's done the mapping of the streams. We also got the drainage line and the catchment. So if I put the drainage lines here, you'll see, let's make them I'm going to deviate from convention and make the drainage lines orange. And there you can see they're right on top of that blue flow accumulation. There they are. I guess if I make them fatter, we'll be able to see them more prominently. And I've also got the corresponding catchment. So there's a catchment draining to each drainage line. So that's the sort of program that we went through last time. Now we said, okay, we have to calculate height above the drainage. So we have to do things like use the flow direction with the d-infinity option. So I'm going to go into geoprocessing and find the flow direction tool. So this is actually, I could have used TOWDEM tools here, but I had it ready to go with, well, we've done all the watershed delineation with ArcGIS. So the surface raster is going to be my filled elevation one, which I better locate onion 3 FEL. And the output flow raster, I'm going to call onion 3 dnf.tiff to make everything TIFF files. The output drop raster, I'm going to call it onion 3 percentage slope, because it's really slope expressed as a percentage. And I'm going to use d-infinity. So I'm going to run that. So we should get a flow direction result momentarily, and it appeared below the catchment, so let's turn those off. There is the flow direction result that we got, and it kind of gives you this, it's actually showing the percentage slope, but the flow direction one gives you this sort of funky looking hillshade approach. We can open the history and we can look at the Python command, copy the Python command, and go to our Python program and paste that at the bottom. And the reason I'm doing that is because we actually, what I said, extend the program. So we've seen how it works. We can extend the program and probably go back and sort of tidy up this program. We don't need to be using this full path here. We can sort of shorten some of these things. But we can see, for example, it's got normal, and then it's got the dnf as a method there. So I'm getting a little bit short on time, so I'm not going to tidy up that program. I'm just going to do the next step. The next step is the distance function, flow distance, and we're going to input the stream raster, which was one of the things that we evaluated from our previous program, onion 3 stream. The surface raster is the filled elevations, where is that? I guess we have to onion 3 FEL. The output raster, I'm going to call it, just to be consistent with the paper. Well, this is actually going to be our hand result. So onion 3 hand. And the input flow direction raster is going to be the dn flow direction we calculated. We're calculating vertical distance. We're using d-infinity, and there's an option to go with the sort of minimum, maximum, and average weighted mean. So I'm going to go with the weighted mean. That was the one I explained where it does the proportioning. The minimum basically picks the shortest path, and the maximum picks the longest. So I'm going to now do the run of that, and this is actually now calculating the height above the nearest drainage for Onion Creek. And once it finishes, I'll be able to open the history and do the same thing about copying the code into my program to effectively have a computer program that does it. And once you've put the code in there, it probably behooves you to try and run it through again, just to make sure that it's all right. I'm going to then, while it's running, I'm going to hone in on a particular catchment. I think we said, so let's, I think we said we were interested in this particular catchment. Was that the one that I focused in on, or was it that? This one there was that I've got illustrated in the exercise on page 13, because that's one where there were actually some houses flooded. So now my height above nearest drainage has completed. I'm going to go back and, well, I'm going to change these catchments so that they're transparent, but we still got the gray lines, and I'm going to select just that catchment because we're going to work just on this catchment. And we can see that we've got the height above nearest drainage is this layer there that you can sort of see. There's the low black values next to the streams, and it gets to the gray shade away. And it sort of delineates according to the catchments because at the catchment boundaries, the height going one way off the divide and going the other way from the divide is different. So let's find all of the addresses in this catchment. So here I'm going to do effectively, okay, well, I'm going to export that catchment as something that I'm going to call just catch poly select, make sure that I know where I'm putting it. Well, I'm just going to let it go into the default geodatabase. So I've created that polygon representing that single catchment that I could show with some sort of a bright color. There's the catchment that we focused on. Now we're going to try and get the addresses that are just within this catchment. So I'm going to select by location, and the features I want to select are the address points that are completely within. The selecting feature is my catch poly select. And if I run that, I will get a set of select. I should have had the address points up, but here it's selected these address points within that catchment. I'm going to export those. So from the address point, I'm going to say I'm going to call that address point select, and save that. So now if I clear my selections, turn off the address points, I've just got the address points in my catchment that I'm focusing in on, so I can sort of zoom in on that. I want to figure out how high these are above the stream. So if I've got a height above nearest drainage, I can identify which ones are flooding. So there's an extract values to points function. So extract values to points. The input point features are going to be my selected addresses. The input raster is going to be hand. I'm just going to call the output result and I'm going to put it in the Onion geodatabase as hand point, and I run that. So now let's look at the attribute table of this. So there's 4,180 of these, and it's got the raster value that it got out of the hand. So I can actually sort those in ascending order. The lowest one is 2.38 meters above the stream. Then there's one that's 7.2. So if I click on that, somehow we find that point. This poor address point in there is deep trouble. It's right close to the stream. But I can move it up, and I see that there's the next one is 7. Next one is 8, 8. Well, if I select all of the ones within a certain range, and if I get my shifting and controlling done right, and zoom to the selections, you'll see there I'm sort of starting to pick off these address points that are close to the stream. And now if we have worked out, say, a flood height that's maybe 9 meters. Now that's a pretty big flood, but they did actually have a very big flood that caused the study. It was something like 30 feet, which is close to 9 meters. These are the places that are going to get flooded. So I think what we've asked you to do here is show and make a layout of all of the address points that are less than 9 meters, and we're saying, well, we're assuming that we'd done the calculation and worked out that the height above nearest drainage was going to be 9 meters, and that would be a map of the places that could get flooded. So, and you can actually work out the depth, because you can take 9 meters minus that value, and you can figure out if it's where they're going to have to rescue people from the roof, which is more likely the case in the 2 meter case, or if it's you can wade in. If it's a sort of 8.5 meters, if it's less than that, you can be comfortable sort of wading into the water. So that was kind of the gist of that exercise. And I think once you've got these raster values here, you can calculate the heights, and then it's a matter of just tidying it up and making a nice layout to tell the story. So that was all that I wanted to show you there, and I guess that brings us to the sad point of the class, where it's just about the end. Are there any questions from anybody out there before we, or in here actually, before we sign off? Okay, well, there's a chat. Okay. Could you please explain how Nibbling works. What is nibbling? I actually don't know what nibbling is. Is there a geoprocessing function for nibbling? Nibble. Input raster mask. So nibble is apparently replace the cells of a raster crossing with the value of the nearest neighbors. I guess I'm not going to be able to give any more deeper explanation than reading whatever's there. I might be able to interpret what's there as I read it live, but I haven't worked with nibble before. But apparently it appears to be useful for selecting areas. It's full, so it's used to fill missing data with the nearest value. It allows selected areas RAS to be assigned the value of their nearest neighbor. It can be used to replace a few individual cells. So I guess if you've got data that's got gaps in it, it's probably quite a useful function. Okay. And hopefully you just run it using the syntax described here. And if you want to do it from ArcGIS, you do something like this code sample. Okay, any other questions? All right, well, if not, thank you all, and I will look forward to seeing your work in the homeworks that comes in, and then I'll respond to them and give you some feedback. But that's it. Thank you very much.